Hello everyone, welcome to my lecture. Today we will be discussing about vector spaces. Yes, so vector space. This is from linear algebra, vector space. Okay, so vector space. You can see the definition. A vector space or linear space V. Another name, linear space, denoted as V over a field F. A field is also required for that. Okay, is a set V together with two operations. Okay, together with two operations, vector addition and scalar multiplication that satisfy certain axioms. Okay, so vector space means what? Over a field F, it is a set. Okay, it is a set denoted as V together with two operations. We need two operations. First one is vector addition and second one is scalar multiplication. Okay, it should satisfy certain axioms. Okay, so you can see the first one. The first is addition, vector addition. Okay, so this addition is a function from V cross V to V. Okay, V cross V to V. You can add two elements from V. Okay, the result will be another element in V. Okay, and this is the symbol for that multiplication, this dot. Okay, this is from f cross V to V. Okay, f cross V to V. Let's see what are the axioms that should be satisfied to become a vector space. Okay, you can see two set of axioms here. Okay, two set of axioms. This is the first set, four axioms under the first set, and this is the second set, four axioms under the second set. Okay, let's see the axioms. First one. Okay, so the first four axioms are regarding that addition. Okay, regarding that addition, and then the last four, both addition and multiplication are coming. Okay, see, first one, that addition is commutative. That means for every alpha beta belongs to that V, alpha plus beta will be equal to beta plus alpha. That is the first condition to become a vector space. Okay, look at the second condition. Okay, B, that is that addition plus is associative. That means for all alpha, beta, gamma belongs to that V, alpha plus beta plus gamma is equal to alpha plus beta plus gamma. Okay, that is the second one. Next, C, the third one, there exists a unique vector 0 in the set V called 0 vector. And what is the peculiarity of this vector? Such that alpha plus 0 will be equal to alpha itself for every alpha belongs to V. Okay, you can find the existence of such an element known as 0 vector. Okay, next one, D. For each alpha belongs to V, there exists a unique minus alpha also belongs to V. Okay, such that the sum of them, alpha plus minus alpha, will be equal to 0. Okay, so these are the first four set of condition. Next, let's move to the second four set of conditions. Okay, second four set of axioms. First one, A, there exists one belongs to that F, our field F. Okay, so we have a vector space V and a field F. This is the vector space V over a field F. Okay, so this one is coming from that F. What is the peculiarity of this one? Such that one alpha or one dot that alpha. Okay, here we are doing that multiplication, scalar multiplication, the second operation. Will be equal to what? Will be equal to alpha itself for all alpha belongs to V. Okay, this is applicable for all elements of V, for all vectors from this V. Okay, next second condition, C1, C2 of alpha will be equal to C1 of C2 alpha. Okay, from where this C1 and C2 are coming? C1 and C2 are coming from F. These are constants. Okay, these are scalars. Okay, and alpha belongs to that V. For all alpha and for all C1, C2 belongs to F, you can see this property. Okay, now move to the next one. C of alpha plus beta, or C into alpha plus beta will be equal to C alpha plus C beta. Okay, this will happen for all C belongs to F and for all alpha beta belongs to the vector space V, the capital V. Okay, next the last one, C1 plus C2 multiplied by alpha will be equal to C1 alpha plus C2 alpha. Okay, for all C1, C2 belongs to F. For all, this is applicable for all for any two elements from this field F, and for all alpha belongs to B. Okay, if they are satisfying all these conditions, we can say that this V is a vector space over a field F. Okay, so this is simply a vector space. Let's see some examples for vector space. You can see some examples for vector space here. Okay, first one, take V as R square. Okay, R is the set of real numbers. Okay, so take R cross R. Okay, you can take that as V, and in that case you can take the field as the set of real numbers itself. You can see this is a vector space. This will satisfy all the conditions of vector space. Okay, if you take this V as R square and the field F as R itself. Okay, we will prove it here. Okay, we have the proof for that. I will show you that. So this is the first example, and you can see many more examples. You can take V as R cube, R cross R cross R. Okay, set of triplets. Okay, and again you can take this F as R. That also will satisfy all the properties of vector, all the axioms of vector space. Okay, so this one is a vector space. R cube is a vector space over the field R. Okay, next one, not only for R square and R cube, for any, okay, for any R raised to any natural number n, you can see all the properties of vector space all over the field R. Okay, and not only for real numbers, you can take the V as the C set of all complex numbers, and you can take the field as the real numbers R itself. That also will satisfy all the properties of that vector space. Okay, next example, take V as again the complex numbers, and F also you can take as the set of complex number. That also will satisfy all the axioms of vector space. Okay, yes. So in the next step, in the next part, I will prove how this first example is a vector space. Okay, let's see how this one, okay, V as R square and field F as R, how this is satisfying all the properties of vector space. Okay, remaining all you can try. You can see that also in the almost in the same way will satisfy all the conditions of vector space. Okay, let's take the first example now. Okay, first example, the first one. Here what is V? Here our V is R square, R cross R. Okay, and our field F is R only. Okay, set of all real numbers. Okay, now let's see how it is satisfying the first property. Okay, how it is satisfying the first property. Okay, we have two set and two set of axioms we have. Okay, we have two set of axioms. Under the first set, we have four. A is here, then B, C, and D. Similarly, we have second set also. In second set also, we have A, B, C, and D. Okay, exactly same as what we discussed here. Okay, first set of four, second set of four. Okay, yes. So see, what was our first axiom? The first one in the first set. Okay, that means that plus that addition is commutative. That means alpha plus beta will be equal to beta plus alpha for all alpha beta belongs to B. Let's see how this is satisfying in our first example. V is R square and F is R. Okay, let's see how that is satisfying here. Okay, property number A, first property A. Okay, suppose alpha, let alpha equal to x1 comma y1. We know that it is coming from R square. Okay, R cross R. So all the elements here are in the form of ordered pairs. Suppose alpha is x1 comma y1 and beta is x2 comma y2. Okay, ordered pair x2 y2. Alpha beta is coming, they belongs to R square. These are two arbitrary elements from R square. Okay, now see what is alpha plus beta. That is nothing but x1 y1 plus x2 y2. Okay, You can add the ordered pairs here. First x1 plus x2. That is what you can see here. Comma. Then y1 plus y2. That is what you can see here. Okay. That means we know that addition is commutative. So x1 plus x2 can be written as x2 plus x1. Similarly, y1 plus y2 can be written as y2 plus y1. That's what you can see here. This can be written as x2 plus x1 comma y2 plus x2 plus x1 comma y2 plus y1. Okay, that means what? Here again you can separate them. That is x2 comma y2 plus x1 comma y1. Okay, this simply means this only. If you add them, you will get this. Okay, and what is x2 comma y2? That is nothing but beta. And what is x1 comma y1? That is nothing but alpha. Okay, so alpha plus beta can also be written as beta plus alpha. That means the first property. Okay, first property is satisfied here. Alpha plus beta equal to beta plus alpha for all alpha beta belongs to B. Okay, so here alpha and beta are arbitrary elements. That means this is true for all alpha beta belongs to our R square. Okay, that means the first property is satisfying here. Okay, now move to the second one, B. B in the first set of axioms. Okay, what was B? See here, that means that addition is associative. That means for any alpha, beta, gamma belongs to B, alpha plus beta plus gamma will be equal to alpha plus beta plus gamma. Okay, let's see how that is satisfying here. Suppose alpha equal to x1 comma y1, beta equal to x2 comma y2, and gamma equal to x3 comma y3. Okay, alpha, beta, gamma are arbitrary elements of R square. Okay, see what is alpha plus beta plus gamma. Alpha can be written as x1 comma y1 plus inside bracket beta plus gamma. Beta is x2 comma y2 and gamma is x3 comma y3. That means x1 comma y1 plus this you can add here x1 plus x3. That's what you can see here, comma y2 plus okay y3. Here x2 plus x3 and y2 plus y3. Okay, order per x2 plus x3 comma y2 plus y3. Okay, that now in the next step you can add them. Okay, this bracket you can directly add like this. See what will happen there. So x1 plus x2 plus x3. That's what you can see here, x1 plus x2 plus x3, comma, similarly this y1 plus y2 plus y3, okay, y1 plus y2 plus y3. And we know that addition is associative. So here you can apply the associative property. That means x1 plus x2 you can put in a bracket and x3 separately. Similarly, y1 plus y2 you can put in a bracket and y3 separately. Okay, that means what? Here you can separate them. That is nothing but x1 plus x2 comma y1 plus y2 plus this x3 comma this y3, because the sum of this thing is only this one. Okay, so this one can be written as this form. Okay, if you add them you will get the same. See, x1 plus x2 plus x3, that's what you can see here, and y1 plus y2 plus y3, that is here. Okay, so this can be written in this form. That means, see, this is x1 comma y1 plus x2 comma y2, right? x1 comma y1 plus x2 comma y2. Sum of this x1 plus x2, that is here, and y1 plus y2, that is here, and that x3 comma y3, no change for that. Okay, so this is what x1 comma y1 is alpha plus x2 comma y2 is beta plus and gamma outside x3 comma y3 gamma. Okay, so this is nothing but alpha plus beta plus gamma. Okay, so alpha plus beta plus gamma is nothing but alpha plus beta plus gamma. That means the associative property is satisfied here. The second one, associativity is satisfied here for all alpha, beta, gamma belongs to B. Okay, alpha, beta, gamma are arbitrary elements, so it is applicable for all elements in the R square. Okay, our V is R square in this example. Now move to the third one, the C. There exists a unique vector u in our V, in this case R square, okay, called zero vector, such that alpha plus 0 equal to alpha for all alpha belongs to B. See, which is that zero vector in our example? Let alpha equal to x comma y, an arbitrary element from R square, and we are taking this zero vector as ordered pair 0 comma 0, because 0 comma 0 obviously we know that it is an element of R square origin. Okay, so that means let's add them. Let's add this 0 plus alpha. That means 0 comma 0 plus x comma y. So 0 plus x comma 0 plus y. 0 plus x is x only and 0 plus y is y only. You will get x by itself. That is nothing but alpha only. That means alpha plus 0 equal to alpha only. Same way you can find alpha plus 0 is also alpha. 0 plus alpha is also alpha. Okay. For all alpha belongs to r square. 0 is also r square. Okay. So that means the third property is also happening here. Third axiom is also satisfying here. Okay. Yes. Next one. The D part. For each alpha belongs to V, there exists a unique minus alpha belongs to B, such that alpha plus minus alpha equal to 0. Okay. This will happen in this case also, you can see. Okay. Suppose our alpha is property D. Okay. The fourth property in the first set. Suppose our alpha is x comma y belongs to R square, an arbitrary element from R cross R. Then define this minus alpha as minus x comma minus y. We know that that also belongs to R square. Okay. So what is the sum of them? Alpha plus minus alpha becomes alpha means x comma y plus minus alpha means minus x comma minus y. Okay. So add them x plus minus x. This will happen here and y plus minus y here. Okay. X plus minus x means x minus x. This becomes y minus y. X minus x 0, y minus y 0. You got 0 comma 0. That is the 0 vector. That means alpha plus minus alpha is 0. That property is also satisfying here. Property D. For each alpha belongs to B, there exists unique minus alpha belongs to B such that their sum will be equal to the 0 vector. Okay, that's what we have seen there. So all the first four properties are satisfying here. Now move to the second one. Okay, the second set. There exists one belongs to F such that one alpha equal to alpha for all alpha belongs to B. Here our F is what? Here our field is set of real numbers itself. We know that 1 is an element of that real number. Okay. And you can see this property with that one. That also you can see the, okay. See. Second one, 1 belongs to our F. Capital real numbers. Our F is real numbers here. Take any alpha, xy belongs to R square. You can see 1 alpha means 1 into x comma y. That means 1x comma 1y. You can multiply them separately. 1x is nothing but x only, 1y is nothing but y only. So x comma y itself you will get. That is nothing but alpha. So 1 alpha is alpha itself. Okay. Similarly, you can see alpha 1. Alpha into 1 is also alpha. So that property is also satisfying here. Okay. We have a 1. If you multiply it with any element in our vector space R square, in our V R square, you will get the same element itself. Okay. So that side property also you can see here. That property is also happening here. Now B1, B in the second set. Okay, B. The C1, C2 into alpha will be equal to C1 into C2 alpha. For any C1, C2 belongs to F, in this case R, and for any alpha belongs to V, in this case R square. Okay, so let's see. Suppose C1 comma C2 are two elements of real number, any two real numbers, and alpha equal to x comma y belongs to R square. Okay, belongs to R square. So see what is C1, C2 into alpha. This can be written as C1 into C1, C2 into x comma y. Okay, because alpha means x comma y. That means this C2 you can take inside. Okay, so C1 into C2x comma C2y. Okay, what is C2x comma C2y? That is nothing but C2 alpha. So this can be written as C1 into C2 alpha. Okay, so C1, C2 into alpha is C1 into C2 alpha. Okay, so that property is also satisfying here. B. Okay, B in the second set. C1, C2 alpha is equal to C1 into C2 alpha. For all C1, C2, these are arbitrary elements we have taken the, so this is applicable for all elements in F, in R and the R square. Okay. Look at the third, the C, axiom C in the second part. C of alpha plus beta, or C into alpha plus beta is C alpha plus C beta. For all C belongs to F and alpha beta belongs to V. Okay, let's see the proof here. Let C belongs to our any constant, any real number, and alpha equal to x1 comma y1 and beta equal to x2 comma y2 belongs to R square. Okay. Now let's see what is C alpha plus beta. That is nothing but C into alpha can be written as x1 comma y1 plus beta can be written as x2 comma y2. Okay. So C into this is nothing but x1 plus x2 comma y1 plus y2. Okay. That means now you can take C inside. So this becomes C into x1 plus x2 comma C into y1 plus y2. That means this C again you can take inside this bracket. So this becomes Cx1 plus Cx2 comma here Cy1 plus Cy2. Okay. That means Cx1 plus Cx2 comma Cy1 plus Cy2 is nothing but Cx1 comma Cy1 plus Cx2 comma Cy2. Okay, sum of this one is only this one. Okay, Cx1 plus Cx1, that's what you can, sorry, Cx1 plus Cx2, that is what you can see here, and Cy1 plus Cy2, that is what you can see here, same sum only. So you can write it in this form. Okay, so that's how we get this step. Okay. Okay. uh, yes. Okay, so this can be written in this form. So that means this one here, from this you can take C outside. So Cx1 comma Cy1 becomes Cx1 comma y1 plus this also becomes Cx2 comma y2. This x1 comma y1 is nothing but alpha and x2 comma y2 is nothing but beta. So this can be written as C alpha plus C beta. That means C into alpha plus beta is C alpha plus C beta. That is our second last property. Okay, and the third one in the second set. Let's move to the last one in the last set, our D. Okay, what was our axiom D in the second set? See here, C1 plus C2 into alpha is equal to C1 alpha plus C2 alpha. For all C1, C2 belongs to F and alpha belongs to C. Sorry, alpha belongs to B. Okay, so take any two real numbers. Our F is R here and our V is R square. Take any alpha from that. Okay, let's see how that is happening here. So C1, C2 belongs to R and alpha equal to xy belongs to R square, an arbitrary element from R square. Okay, now C1 plus C2 of alpha will be equal to C1 plus C2 into xy. Okay, alpha is xy. Okay, C1 plus C2 into xy. That means you can take the C1 plus C2 inside. So this become C1 plus C2 into x. That's what you can see here, comma C1 plus C2 into y. Okay, that means you can take this x inside. This becomes C1x plus C2x. And you can take this y inside. So this becomes C1y plus C2y. Okay. So this one can be written in this form, right? Because if you take the sum of this, you will exactly get the same. Okay. C1x comma C1y plus C2x comma C2y. That is C1x plus C2x. That is what you can see here. Then comma C1y plus C2y. That is what you can see here. So this one can be written in this form. Okay. Okay. So that means, yes, this one can be written in this form. Okay. This step, and that's how we can find this step. From this, you can take C1 outside. So this becomes C1 into x comma y plus from this take C2 outside. So C2 into x comma y. That means C1 into x comma y is alpha and C2 into x comma y here also alpha. So C1 alpha plus C2 alpha. That means C1 plus C2 of alpha is C1 alpha plus C2. That means the last property is also satisfied here. The last property of vector space we found just now. Okay, that means all the properties, all the axioms of vector space are happening in this example, in example number 1. So this is, that's why this is a vector space. Similarly, you can find the same axioms in all the other examples. Okay, and try it yourself. Okay, I hope it's clear. We will discuss more about vector space in the upcoming sections. Okay, so thank you so much for watching. Bye bye.